So we're going to talk about sequences. The first section of Chapter 9 is just going to go, first part, you guys have talked about sequences back in Algebra 2. So just to go over a few things about sequences, we talk about an infinite sequence, or just a sequence. It's an unending succession of numbers, and these numbers are called terms. It is understood that terms have a definite order. So for example, the first term we can call a sub 1, the second is a sub 2, and the third is a sub 3. So that subscript tells you the position number of the term. The dots, remember when you list your terms, indicate that the sequence continues indefinitely. If there is a pattern, then you can write the general nth term formula. A sequence, if you remember from Algebra 2, can be specified by two different formulas. One is your explicit, or recursively. For what we're going to be focusing on with the sequences, we'll be looking at the explicit formula. There are two ways that you can write your infinite sequence explicitly. One is by just doing a listing. So you list the first 4 or 5 terms, dot, 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 comma, and then you put your explicit formula, followed by, again, you must include those dot, dot, dots in the end. That's how you show that it goes on to infinity. You may also see brace notation. So you see your explicit formula inside your braces. Typically, most formulas start with, or sequences start with 1. Some will start with 0. But then you can see it's going to go on to infinity because you have the infinity sign right there. So those are two different ways when you're asked about infinite sequences explicitly. You may see them one of those two ways. Remember, a sequence is a function whose domain is a set of integers. So you may have a sequence, if you look at the graph, your first, second, third, fourth, 10th. Notice it's increasing without bound. You may have terms that actually we call, when n is equal to 1, you go to 1. When n is equal to 2, you go to -1. 3, you go to +1. 4. We call this an oscillation. What's happening is with this particular sequence, the terms are oscillating between -1 and 1. You may have a sequence that is actually increasing, but then it approaches a certain value. So notice these terms in this sequence, first term, second term, third term, fourth term, fifth term, they are approaching 1. It appears when you look at this one, you may have a case where this sequence, it's bouncing back and forth, but notice it is converging towards a particular number. It oscillates prior to the limiting value. So it may start off oscillating, but then eventually approaches a fixed number. The limit of a sequence is describing how a sub n behaves as n approaches infinity. The sequence may approach a limit, which we'll call L. If the terms of the sequence eventually goes towards a number, then we say that the limit is going to be converging. If the limit does not converge to some finite limit, then we say the sequence will be diverging, or the limit diverges. Like I said, this may start off oscillating, but what we care about is the behavior as you're approaching infinity. What's the pattern as your n values are getting larger and larger? So here's some more examples graphically that what could happen. So again, when you take a look at this one, this would be diverging by an oscillation. Here we can see as your n values are getting larger and larger, it is converging in this particular example to a fixed limit. So we would say that this is converges towards L. However, these particular terms are as n approaches c, but f of x is diverging by oscillation as n is approaching infinity. If a limit converges, then we can apply some very familiar properties of limits to sequences. So again, here's again a review of your constant rule for limits. You can pull your constant out and then multiply it by the limit. So again, these are all your properties limits. If you want to find the limit of a sum, you can take the limit of each term and then add them together. These theorems allow us to also use L'Hopital's rule. in difficult cases, determine the convergence or divergence of a sequence. To apply L'Hopital's rule, remember, you must consider the differentiability of the function. And one thing is the squeeze theorem that happens with sequences, or we also call it the Sandom theorem. So suppose you have the a sub n, b sub n, c are sequences such that a sub n is less than b sub n less than c. If your sequences a sub n and c sub n have a common limit as n approaches infinity, then b sub n also has a limit as n approaches infinity. So in other words, notice what you're having. You have this limit that is approaching, the values of the sequence are decreasing and they're approaching a fixed limit. However, these terms are increasing but also approaching the fixed number. So for example, if you take a look at this sequence 1 over n is equal to 1 to infinity. If you wanted to find out whether or not this limit converged or whether it diverged, you can find the limit as n approaches infinity of 1 over n. And that is going to be approaching 0. Now if you take a look at another sequence, negative 1 over n is equal to 1 to infinity, and I want to find the limit as n approaches infinity of negative 1 over n. That is also approaching 0. So that's an example. All these terms in the sequence would be negative, however, they're still approaching that fixed limit of 0. All these terms in this sequence are positive, but it's also approaching 0. So that's what they're talking about with the squeeze theorem. So some sequences are going to have alternating terms, positive, negative, positive, negative. So when you take the limit of a sequence with alternating signs, the property of an integer is being either odd or even. That's when we talk about a parity. So for example, negative 1 to the first, negative 1 to the third have the same parity. Even though their base is negative 1, both their exponents are odd, we would say this would have an odd parity. Both were going to produce a negative 1 as their output. Or if you look at negative 1 to the second and negative 1 to the fourth, both these negative 1s are raised to an even power, so we would say that this also has the same parity, which is an even parity. These would both produce a positive 1. So for example, if you have negative 1 to the n and negative 1 to the n plus 2 have the same parity, this would make a sequence start with a negative number. Again, assuming that the sequence starts at n is equal to 1. Negative 1 to the n plus 1 and negative 1 to the n plus 3 will have the same parity. This would make your sequence start with a positive number. So here's an important theorem when we're talking about sequences and we want to know the convergence or divergence of an alternating sequence. If you can find the limit as n approaches infinity of the absolute value of n equals 0, then the limit as n approaches infinity of a sub n will also be equal to 0. This will converge. The contrapositive is true. If the limit as n approaches infinity of a sub n is not equal to 0, then the limit as n approaches infinity of the absolute value of a sub n is not equal to 0. So let's write out the first 5 terms of the sequence and determine whether the sequence converges or diverges. If it converges, we're going to find the limit. So first of all, let's go ahead and let's write out our first 5 terms. So starting with 1, I'm going to plug in 1 for n. So I'll have 1 over 3 times 1 is 3 minus 1 is a 2. Plug in a 2. 2 over 3 times 2 is 6 minus 1 is 5. Plug in a 3. That's going to give me 3 over 8. Plug in a 4. 4 over 4 times 3 is 12 minus 1 is 11. And then finally plug in 5. 5 over 5 times 14. So there are the first 5 terms. So then to find the limit, I'm going to take the limit as n goes to infinity of the n over 3n minus 1. So now if you remember these limit rules, you're going to be looking at your horizontal asymptotes. Remember your rules of the horizontal asymptotes, just to review. Remember, if the degree of the numerator is less than the degree of the denominator, then it's going to be a limit equal to 0. If the degrees are the same, then the limit will be a ratio of the leading coefficients. if the degree on the top is larger than the bottom, there is no limit. That's where you'd have the slant asymptote. So again, if you look here, the degree of the numerator is a 1, the degree of the denominator is a 1, so this limit is going to be 1/3. So we would say the sequence converges. It's converging to a value of 1/3. So now let's take a look at B. Let's write out the first 5 terms. I'm going to plug in 1 for n, so that's going to give me a sine of pi over 1. Plug in a 2, 2 times the sine of pi over 2. Plug in a 3, 3 times the sine of pi over 3. Plug in a 4, 4 times the sine of pi over 4. And 5 times the sine of pi over 5. So now to figure out if this is converging or diverging, we want to find the limit as n goes to infinity of n times the sine of pi over n. This is where using L'Hopital's rule, when you have a more complex limit, is going to help you. But remember, L'Hopital's rule only works if you have a ratio. So I can take this n, and I can rewrite this as the limit as n goes to infinity, sine of pi over n, divide this by the reciprocal of n, which is 1 over n. So now if I want to go ahead and try and find the limit as n goes to infinity, pi divided by a really, really, really large number is going to 0. And I know the sine of 0 is 0. 1 divided by a really large number is 0. That's also going to go to 0. So remember, L'Hopital's rule only works if you get the indeterminate form of 0 over 0, infinity over infinity. So I can apply L'Hopital's rule. So remember, L'Hopital's rule, I'm going to take the derivative of the numerator and divide it by the derivative of the denominator. So I have the limit as n goes to infinity. Now to find the derivative of sine pi over n, you're going to have to apply your chain rule. Outer function is sine, so that's going to be the cosine of pi over n, times the derivative of the inner function. So the inner function is going to be, remember, you can write this as pi times n to the negative first. So again, this is going to become negative pi over n squared. Now I have to take the derivative of the denominator. So the derivative of the denominator, I can rewrite 1 over n as n to the negative first. So that's going to be negative 1 over n squared. So I can rewrite this as the limit as n goes to infinity, cosine pi over n, to simplify this fraction, times negative pi over n squared. I'm dividing by negative 1 over n squared, which means I'm going to multiply by the reciprocal of negative n squared over 1. So these n squares are going to cancel, so are the negatives. So now I'm going to find the limit as n goes to infinity, cosine of pi over n times pi. Well, pi is a constant divided by a really, really, really large number. This value in here, as n is approaching infinity, this pi divided by a really, really, really large number is going to get close to 0. So this is approaching 0. So cosine of 0 times pi. Well, I know cosine of 0 is 1. 1 times pi is pi. So then this limit's going to be converging towards pi. The last page here, again, you've got the negative 1 to the n plus 1 times 1 over n. So again, if I want to write out the first 5 terms, again, when I plug in 1 for n, well, 1 plus 1 gives me an exponent of 2 here, so that's first term is going to be positive. So 1 over 1 is just a 1. Plug in a 2, so that's going to give me an exponent of 3, so the next one's going to be a negative number, so that's going to be a negative 1 over 2. Again, the next term is going to be positive, so when I plug in a 3, that's going to be 1/3. Next term will be negative, that'll be negative 1/4, and then the positive number will be 1/5. So what I want to do, since this is an alternating sequence, what I want to do is check for the limit as n approaches infinity of the absolute value of a sub n and see if it equals 0. So what happens when I'm taking the absolute value, this negative 1 to the n plus 1 is my alternator. So when I take the absolute value of this limit, I'm going to drop the alternator. So what I want to find is the limit as n approaches infinity of 1 over n, which is equal to 0. So that I know this limit's going to be converging. And if you look at the terms that I wrote out, you can see you've got a positive 1, a positive 1/3, a positive 1/5, and a positive. Notice all your positive numbers are approaching 0. They're just on the positive side of the x-axis. But if you look at your negative terms in the sequence, you have negative 1/2, negative 1/4, negative 1. They're also approaching 0. So that's why this limit exists. So now let's take a look at D. Again, you have another alternating sequence. Again, starting with 1, this is going to give me negative 1 to the first, which is going to give me a negative number, so the first term is negative. When I plug in 1, 3 plus 1 is 4, which is going to give me 4. And because it's negative, it'll give me a negative 4. When I plug in 2, 6 plus 1 is 7, that's going to give me 7/2. Next one's going to be negative, so that's going to give me 10/3. When I plug in 4, that's going to be another negative number, so that's going to give me negative, it's a negative 10/3, excuse me. This will be positive, I'm sorry, positive 13/4. So negative, positive, negative, positive. And then the next one will give me a negative 16/5 when I plug in 5. Because remember, we're starting with a 1, that's giving me a negative 1 to the first, which is going to give me a negative number. When I plug in a 2, that makes it positive. When I plug in a 3, negative. So we have the signs correct. Now, since this is an alternating sequence, I want to check to see the limit as n approaches infinity of the absolute value of a sub n, check to see if it's equal to 0. So I want to find the limit as n approaches infinity. I'm taking the absolute value of this sequence, so I'm going to drop the alternator of 3n plus 1 over n, which is equal to 3. That does not equal 0. So again, what's happening here, this is going to be diverging. Since that does not equal 0. Again, what you can see here is you can see that your positive numbers are going to be approaching a different number than the negative numbers. So here they want me to find the general term, so here we have to write the explicit formula and then determine if the sequence is converging or diverging, and then if it converges, find the limit. So again, it's helpful to look at your pattern, 1, 2, 3, 4. We're starting with the first term, so you can see what the pattern is going to be to produce the terms in the sequence. Notice the numerator is 1 less than the position number, so it's going to be the position number minus 1. Over, here's my first term, second term's being squared, third term's being squared, fourth term's being squared in the denominator. So that's going to be an n squared. So what I want to do is find the limit as n approaches infinity of n minus 1 over n squared. Degree of the numerator is less than the degree of the denominator, so this is converging towards 0. So now notice this is an alternating sequence. This is your first term, second term, third term, fourth term, fifth term. And there is more than one correct alternator that you can use in a formula. Typically we use a negative 1 to the n or a negative 1 to the n plus 1. So when you're trying to use an alternator, you'll include a negative 1 to the n if your sequence starts with a negative number. And again, this is assuming your sequences are starting with n is equal to 1. You'll include the alternator negative 1 to the n plus 1 if your sequence starts with positive numbers. So since this sequence is starting with a negative number, I'm going to include the negative 1 to the n as part of my sequence. So my explicit formula then is going to be a sub n is equal to negative 1 to the n. That takes care of my alternating signs. I have 1, 2, 3, 4, 5. That's just going to be negative 1 to the nth times n for my explicit formula. Now to find the limit as n goes to infinity, I want to take the absolute value of negative 1 to the nth times n, which means I drop the alternator, so the limit as n goes to infinity of n. That's not approaching anything, that's approaching infinity, so we would say this is diverging. So now here we have, this is 1, 2, 3, 4. So now if I want to flip this around, again, notice this is a positive number, positive number. I can rewrite this. You can kind of see the pattern. This is a 1 over n minus 1 over n plus 1. But if I rewrite this formula, I can rewrite this as a -1. I know I have to include an alternator because this is a positive number, this is a negative number, this is going to be positive, negative. So it's -1 to the n plus 1 times. I can write this as 1 over n minus 1 over n plus 1. So now to find whether or not this limit is going to diverge or converge, I want to check for the limit as n approaches infinity of the absolute value and check to see if it equals 0. So the limit as n approaches infinity of 1 over n minus 1 over n plus 1. Now remember your properties of limits. What I can do is I can find the limit as n approaches infinity of 1 over n minus the limit as n approaches infinity of 1 over n plus 1. Well, 1 over n, 1 divided by a really large number, or the degree of the numerator, is less than the degree of the denominator. That's going to 0. Minus 1 over n plus 1 as n goes to infinity. Again, degree of the numerator is less than the degree of the denominator. That's also 0. So 0 minus 0 is 0. So this is converging. And that's it for section 9.1.